Hello and welcome back. Here we are tackling this BlitzBASIC to PlayBASIC converter. In today's episode, we're actually going to look at the lovely Torus that's spinning around on the screen. The current level of the build pretty much puts us at a workable state. Now, it doesn't produce working code for this example, but I'll put it on screen for you, and we'll run it. And it's pretty cool. Okay, let's take a look at the original Blitz code. It was written in 2001, this example, and it's quite a nice example when running, as you've already seen. But the whole thing is all in software. There's no hardware acceleration, no internal polygon rendering in it. All the poly rendering is done, well, brute force really. Drawing a batch of polygons, doing this stuff here, drawing out vertices, sorting the faces, etc. So a lot of work is being done. That's the key point here. That's the takeaway point is that there's a lot of work's being done until we come right down to the software rendering. This example is doing Gouraud shaded polygons. And they're also light source, which makes it look a bit more interesting. What I've actually done is I've taken the original code and attached the data statements because it was selectable in the original. Our translator at the moment doesn't understand include statements, so we couldn't have that set up this way. This way we can just pass it through as one big blob and get a blob out. Back to the translation. So let's run the translator now. We'll run it in normal mode so we can see the speed of the conversion. It's about 1,000 lines, I think. No, sorry, it's 2,000 lines, but most of that is data statements, so don't get too excited. So we're doing our conversion in about 100 and, I'll be generous and say 150 milliseconds. Not bad. If we run it in debug mode, it'll take a lot longer, so it's spitting out a lot of data to the console. We've got about half a second there all up. So the console is over here. That's our code that's been translated. The data statements didn't need to be translated at all, so they've just passed through. Where are we? Our program code up here has been converted. Go up the top, we can see that's the start of our code, and above this is the information about the scopes, what local variables there were, how many times they were used, etc. Some are used very frequently, some are used hardly ever. I think we'll be able to use that to our advantage and give tips about the conversion for each scope. Yeah, let's not get ahead of ourselves. Let's just get this thing converted. So let's grab all this. Head down the bottom. Yeah, okay. Grab that thing. And quit out of this. Okay, I've already set up an empty project for us to paste into. So let's paste our code from our conversion across. So we're getting 2,700-ish lines of Blitz code. Now, we've got an include file up the front here. Sorry, let's grab that before. We've inserted an include file. This is coming from my own wrapper at the moment to emulate Blitz functions. Let's kind of see how we go. See how far we get without dying. I know some functions here we're going to need to remap, like there's read statements here. PB has a different syntax for data statements. And we've got some collisions there too, but we'll go through them so you can sort of follow what's happening with this stuff. We compile. Right, so our first problem is this read statement. Read in traditional BASIC is a command, and we don't support that. We actually have a read data function to grab the next bit of data off the data. We can think of data like a stack, can't you? It's really just like an index to a table. But so we'll branch ahead. Vertex equals vertex. We've got some data statements there. Put those there. Get rid of those. Thanks. I can see some problems with this already, and they're not to do with the translation, they're to do with differences in well, how one language likes to use keywords and one doesn't. Ooh, undo that, thanks. What did I just do then? Deleted that. Terrible. That's some dummy reads there, so the data's got some empty stuff in it. Don't need the read statements there, of course. Pull them out. Quick save. Let's just see what the next thing it doesn't like about this is. Yeah, I thought it wouldn't like this actually. See how we've got a type name called vertex and an array called vertex. Now it can't really distinguish between the two. Obviously in Blitz you're allowed to do that. Oh, in PB you can't. So what we'll do is we'll put like a lowercase t in front of the type names. And so it's in front of vertex. In front of poly was another one as well. Poly was one. And light source was one. Okay. So like South Park there. You're correct. Yeah, there you go. That was my mistake. Terrible. Ah, here we go. So this is a byproduct of the wrapping. PB likes to its functions to have a pair of brackets on them. Yeah. Oh, okay. Yeah, this is something that popped up when I was doing the AMOS to PlayBASIC conversion. In Blitz, it's valid to have a variable called FPS. In PB, that's the name of a function. So the error's going, hang on, what are you trying to do with FPS? You can't do that with this. So we have to rename this. When I did the AMOS converter, it would just put a prefix in front of these ones. That's what we'll do now. We'll just go, I don't know. Yep. Anything that's FPS, just call it local FPS. Yeah. Got to call it anything we want to do. There's ones over there too, hidden away. Any more? Can't see any more of those, so let's just compile and see how we go. Oh, text. Yeah, text is a bit of a pain. Because of the conversion, I've got a version of text that'll do strings, but here we've got a combination of string data and integer data. So we have to have like a string wrapper around this. For the AMOS converter, I did actually that's actually what I did, is it went through and it did a rough sort of bracketing of these things here, and just assuming that they're integers or whatever. I might just get rid of the wrapping for this command, because text is pretty much text. There's not much. We're just drawing stuff in the current font, but we will have to actually put strings around these. Isn't that terrible? Oh, goodness gracious. Put the closing bracket on. Yeah, it's definitely something that we should definitely try and tackle. And that and the variable collision stuff too, that could be a problem with big code bases. I'd forgotten about that one. Next one, let's just hit compile again, see how we go. Flip, need some brackets. Flip is basically sync. You know, for those in PlayBASIC land, it's just flipping the back buffer for the front buffer. Hey, that's a long way through. Lock buffer. I think in Blitz it requires a parameter, and it's set up to set up so that surface 0 is the screen. So we'll just put lock buffer 0 for now. And there's another collision there. See how it's got RGB equals this expression. Wow, I'm surprised it's done like that. We'll leave that there just to show you that that's going to upset PlayBASIC. See how this variable name here, it's going, hey, you've got a function, you're using the function name in some wacky way. What are you doing? We'll just call it, put an L in front of it for local or something. He compiles, see how far we get. Right pixel. Oh, it's got a surface thing on the end. Put 0 for surface. You know, pretend like we know what we're doing. Unlock buffer. Oh no. 0 for surface. Yep. Good on you. Fantastic. Oh no. Oh, merge sort. So the functions. Yeah. Okay. So at the bottom there, we're exporting a integer, which is a assumed return from the translation. So for this exit function here, we better have the same response. Otherwise, you might get some stack misalignment. There is an error for that actually, if you get one. Press on, dudes. Let's go. Oh. Yeah, some basics will allow you to do if expression and then as long as there's nothing following the then, you can use an end if statement. We don't do that. I must trap this one and cut it out, or just add it to the phraser at some point. Lock buffer, it's going to be the screen, isn't it? Unlock's going to be the screen. Right pixel, 1, 2, 3. BB back buffer, same collision issue there. So that we're constructing a color and then writing it to the screen. So I've got a lot of work to draw a pixel. Yeah, so it's going to run pretty terribly initially, but I know we can speed it up when we get this thing going. Same drama. Don't need the then statements, thanks. Hit a save. We've got through the code. That's cool. Got a dot in front of the label anymore. What else we got? Chords. Compile again. No, one more. Surely that must be the end of the data. Let's hit run. Wow, it's running. And it actually is running, but there's some problems with it, as you can see. And one of the problems is not what you're expecting. I did port this the other day and ran into the same drama, so I know roughly what this issue is going to be. So before we tackle that, I'll just demonstrate we're working. Well, I hope it's working up front. So we won't draw the polygons as ground. We'll just draw them as a set of vertices. The function's already in here. Hopefully it should work. There you go. In other words, the code that handles the rotation, projection, etc., and the poly sorting, that's all actually working. What's not working is this draw polygon function. Yeah. If we cut poly out, put one of these line statements in. Now this has the old syntax. See how it's got the backslash? That's the Blitz syntax. Because this code was inside a comment and this wasn't converted. Quick save. Let's hit run. So we are actually working. That's pretty cool. I like that. And the rate's not too bad either. We're getting, you know, 10s and 15s, etc. We can do better. Now, sorry, I might just put a space bar on this main loop. Where are we? Where are we? I've set an exit time there, so if it runs for a number of frames, it'll exit by itself. I might drop that down to 50 frames. It sounds like a short time, but when we get this, we start tackling this this poly rendering routine. It's very slow initially because of all of the wrapping. It has a few bugs in it too that we've got to actually track down. So it'll run for 50, no, it'll run for 200 frames, 250 frames, okay. Or until I hit the spacebar or the escape key. Spacebar, good. Right, let's tackle this draw poly. Let's go to the Gouraud poly function. I think what we'll do is we'll actually have a look at this. Are we drawing the lines or not? What are we drawing? Right, that's the X from this row. It's the X from the next row, and we'll draw it in like a, I don't know, green maybe. So I should draw a strip for where each horizontal strip of the polygons drawing is. Should. Now, clearly the lines are outside of the polygons because the polygons are these white lines here. And our lines are way outside that. So something's not right. I do know what the problem actually is. So I'll talk you through it, this one here. It's in this edge function where we're relying on, well, let's go back a bit. You might have noticed that all of the values here for coordinates, see how we've got x1 and then we've got RGB coordinates for it. We've got x2 RGB coordinates. These are to draw down the edge of the polygons as it's being scan converted. In other words, when we have a triangle, we work out what's the top point, and we work out what edges we need to draw, and we draw ideally from the top to the bottom. You can actually draw in any order you like, as long as you end up with a bunch of lists, a bunch of spans that represent the shape. Now this doesn't work because here we've got a translation where we're going, we're subtracting x1 from x2 and then shifting it up 8 bits. If x1, x2 are positive, that's fine. And if it's the same goes for y1, y2, if that's positive, that's fine. But if at any point we end up with something that's negative, we're mixing signed arithmetic with bitwise arithmetic. So something between how the shift operator works in Blitz and how the shift operator works in PB is different. Here I'm just moving the bits, just going, hey, shift the bits up, who cares about the sign of it? So we've actually got to do a division here, or sorry, multiplication. So if we shift something, if we shift something up 8 bits, I'll just call it scalar, I guess. So we're just going, we can do it like this. We can compute that scalar. That's the level of precision, which is going to be an integer value of 256. So we can substitute in here. We're multiplying this. Sorry, wrong operator. Now, because PB is interpreted, the cost of having an integer mult or an integer shift is not that great, to be honest. It's really almost nothing. Well, actually, I wonder there too. See how we've got a shift, and then in addition, I wonder if the precedence of this is actually a problem. Let's just check that. Hey, we're here now. Let's just do it. Yeah, come on. I know you're bored. I know you want to see it running fantastic. Yeah. So this is computing our edges. If our edges look normal, then that's our problem. That it's not there's not a difference between the shift. It's a difference between the precedence of the operators. I don't know. Let's find out together. Hey, that's the problem. That's nice to know. Yeah, all right. Just to check that means we can get away with, we don't need to do those modifications. We can just go, yeah, all right, do your thing, dude. Do this. Oh, that's very good. Do this thing. Oh, very good. Lovely. As long as it still works. The slow performance is actually a common problem with direct draw applications. All right, so that's actually solved our problem. So if we go back, that's our pixel rendering loop. That's our line rendering loop. Now if we do something simple, like we go, hey, lock buffer here. So we're drawing all of these lines batched up and we're locking the surface. That should make PB a lot happier when we're doing this job. Should. Yeah, it's much happier with that. Cool. Now we know the vertex locations are accurate. We know that they're all the same. So now we need to tackle this inner loop. And I know this is pretty slow. This could take, quite a while to render. So I'll put that abort case back into the code of, we'll have it be 20 frames. See how bad we get, how bad it runs up front. About a frame a second. But it is running. Can we improve on this? You betcha. How are we going to do it? Well, the same old way we always do it. Locking the buffers, dude. So we know it works, and all of our efforts there have not been in vain. So we'll get rid of the line drawing stuff there for a second. Go up to and draw a polygon, and go have a look at the draw. Ooh, that's right below it. Right. Now, right pixel is pretty much a wrapper around the dot function. So we can substitute right pixel with dot. We don't need to know the buffer all the time. PB will work that stuff out for us. So we could just do this. .c, which is the coloured version for the LRGB, and that should help us out a lot. Doesn't seem like it has though, does it? And the main reason for that is that we are drawing 500 polygons in every scan line of those polygons, which is going to be, let's say each polygon's got 20 scan lines, so that's 570 times 20. That's how many times we are locking and unlocking the surface. That's a lot. So what we need to do, what we should do really, is that rather than lock the buffer every time we draw a strip, draw one span, which is how this has provision for it before, go up to the, and we'll draw these for those. So there we go. Would you look at that? So we're running actual translated BlitzBASIC code. It's drawing every polygon dot by dot. We've got some buffer management control in there. We're drawing lots of extra dots there too, so I bet they don't have great buffer management stuff in them as well. But we're still doing something that's not great though, isn't it? We're locking the buffers every time we draw a polygon. So if we're drawing, the more polygons we draw, in this case here, if we have 500 polygons and half of those polygons are visible, so let's say 250 on average, then we're going to be attempting to lock the buffer and unlock it 250 times. So we want to actually, probably a better solution would be to lock the buffers at the start of the polygon batching and then release it at the end. Let's try that then. So let's draw a polygon routine here. We're running through and doing all this good stuff. So we'll just do the locking it at this level and strip out the other stuff that we added before. Where are we? There we are. So it locks the current surface, by the way, if you're not familiar. Draw vertices. There's no buffer, although there is some there. That's not too bad. Sorry. Let's go to Gouraud polygon, find that thing. We don't need to lock the buffer in here, so we can do our strip, render our strips, and the buffer state is being managed on a higher level, so we don't need to have all this please and thank you at this low level here. That should make it perform much better. Should. And does. Now we're capturing the screen, we're drawing a bunch of dots as well, so you know, it's not bad. It's just a complete translation of the same application. Clearly the inner loop here has some things there we could probably get rid of. Like, if we know that we're never drawing outside of the display constraints, we can swap dot with fast dot. And we probably should do, here I think we're always rendering to the same surface. So that would mean our lock would be appropriate for the same surface all the time. But you've got to be careful with that stuff. One way to ensure that's never going to, always going to work is we can read, if you ask PB to read a pixel from the surface, it will see the locking every time. So we read one pixel at the start of the batch of all the polygons, and then we never need to do it again. If you're jumping around, changing images you're rendering to, locking something, unlocking it, the optimizations that track the lock state can you know, they can work against you. I know, I'm a terrible person. Should be the same. Cool. Well, it's pretty good. Some stuff in here too. You could grab this thing here. Just call it. This is your index. Grab your index from there. Save reading that array 3 times. So we'll read it once and then just throw it away. Those kind of, there's micro optimizations you can run through and do those things yourself. You probably always treat your colors separately and have the light source computed. Or you've got, well, actually, you can clip the range there. For example, C2 equals clip range C2 0 to 255. That sort of thing. You're probably not really winning back any performance by doing those things, but it can just reduce your code. It's pretty cool. I like it. I like it a lot. Right. That's our translation for you. Hope you enjoyed that. Let's say we wanted to push this a bit further. We could make this a bit more PlayBASIC friendly. Get rid of the dot rendering stuff. Draw vertices, get rid of that. Don't really need it. Let's check this thing out. That's nice. One thing we could do is, obviously, since we're in PB land, draw a polygon. Now, let's head down to our draw line, wherever that is. This particular section of code here, it's forming an RGB color. What we couldn't do is we could, of course, use the RGB function, RGB, what was it, RT, GT, and then BT. We don't have to do this in software, so we have 2 function calls that approximate this. We get rid of a shift, and 2 additions, but we substitute them for 1 function call. Let's try it. It's pretty hard to know if we've won much back in that. I would say we probably have. Obviously, the best way to do this in PB is actually to do this. Let's draw a GouraudStrip from X1. From R1, G1, B1 to X2 RGB. It's going to be R2, blue 2, and green 2, and on the Y row, so we can just get rid of all of that, really. Yeah. Pretty comfortable now. It's obviously we're switching a lot of the runtime dependency to command set dependencies, which is because the built-in function for drawing a GouraudStrip is pretty much, well, it's pretty optimal, compared to, I don't know how many cycles this takes to execute through the runtime, but every single pixel's doing that. I guess what you could do is you could use some of the paired pixel optimization stuff where you draw, you unroll this inner loop a bit further, you draw pairs of pixels in one pass, compute them, etc. And that actually works pretty well, to be honest. And you draw a pair of dots at one time rather than a single dot. And that can be beneficial because you're drawing or you're saving some overhead from calling a function, which in the runtime is quite expensive. So even though this is relatively fast, you know, this is the fully interpreted rendering loop. So we're probably somewhere in the, you know, between 30 to 60 frames per second, which is stunning to me, while it's being captured. Or now this is going to be, you know, comparing to the native loop that draws Gouraud pixels, there's not that much detriment. It's probably twice as fast, let's say. If I converted the whole thing to use the Gouraud polygon, it would be much faster again. But I won't. I'll just revert the code back to how it was, and you can tackle this yourself. What if we avoided drawing the line at all and just drew a ground line in here? So we computed the start of the line, x1, yep, go for it. X2 is going to equal, and it's the here. So we just need these RGB values here, and that function should pretty much work the way it was working before. X, Y, X1, Y is the same. Let's try her out. I think for this approach we'll pretty much have maximized our throughput for it to draw strips. To get quicker we're going to have to go to drawing polygons. Just draw the whole thing. Yeah. Grab triangle, x1, y1, RGB1, x2, y2, RGB2, x3, y3, RGB3, exit function to avoid all that other stuff at the bottom there, you know. So RGB1 equals RGB, RGB, G1, B1, because the command expects the parameters to be fed to it as colors that are compressed, so that are packed together as RGB rather than separate RGB fields. Alright, let's give it a go. Goodness gracious. Oh. I've got to return a 0. Yeah, no surprises there, is it? So you can see it kind of peaking at a few hundred frames per second. What if we just keep those in the code? We'll have make 3 different versions of it. So version 2, which will just be the line optimization, and version 3 will be the full polygon rendering thing. So we'll just cut all of that out. So version 3 of the function will be this. Don't need anything below that. Version 2 will be the so we're doing all this work here, great, all going well, and then we're doing this. So we're using GouraudStrip to for this version. Where are we? And for the original version, we just were doing as it was, the stock version. Just restore that to how it was. Cut all that stuff there out again. Excuse this video for being so long. So the inner loop, no, we want the actual pixel rendering. Run it, give it a test. We're back to the normal software rendering, which is still pretty good, isn't it? Cool. What if we put a switch in there to choose which rendering method we wanted? Let's have a global render method equals 0 by default. At the bottom here, we'll just display this to the user. Oh no, we'll draw up there actually. So we'll come down about at row 60, random method. Random method. And just call it render. Yeah, we'll do that. Have a thing on the end here, render. Sorry, method underscore. Come on. I know it's late, but it's not that late. Add a bit of crappy logic up front, you know, all the good stuff. Select render method case 0. Dot. So this is the fast dot in a loop. And select a couple of those. 2. This is the GouraudStrip, Gouraud triangle. So we'll just have a bit of a check here. I don't know if the enter key is pressed or something. Whatever. This, bump that. Put bigger than 2. Make it equal to 0. Let's go with default case. I couldn't be bothered. Isn't that terrible? Now I could use like call function in this and do some asinine kind of crap. We'll just have the polygon rendering stuff wherever that's gone to. Draw poly. Select render method. Have a select case. Very old school. Right, so we were at method 1, method 2. I'll make those correlate here actually. Method 1, method 2. Sorry, I didn't pick the source. It's going, what? What the hell? Alright, so method 1 is the GouraudStrip version, and Polygon 2 is the full-blown Polygon version. Let's try it out so we can check them side by side. Alright, so we're looking at the fast dot, which is the original emulation of the Blitz code. We're switching to GouraudStrip mode, which is we're drawing the inner strips with GouraudStrip command. We're peaking at 125 frames per second. We're averaging around over 60 frames per second now, all in software on the interpreter. So with Polygon, we're hitting 250 frames per second. The average is coming up and up and up. Now, of course, that's going to be quickest because we're passing control from the interpreter to machine code to fill the triangle and come back. I hope this was insightful. Hope you learned something. Hope you're interested in something. Thanks for watching. I'll see you next time. Bye.